to another session for physics. All right, so what we're going to do today is build on our from before. So today is going to be like a projectile motion. Right, so I am doing today I'm using a whiteboard from, it's called tutorialspoint.com. I've been experimenting with things. Earlier I was using Microsoft, and Microsoft has a bad habit of trying to push 360 on everybody. I don't need 360. So anyway, so this is our first one on this. Let's see how it goes. I think there may be some colors here that I might be able to choose. This is probably a color palette. Yeah, so I can use red here. Okay, so what is projectile motion is when you shoot something in the air, so it will go like this and over there come to the ground. So this is the trajectory. And we'll assume that acceleration is pointed down. So acceleration vector is like that. And it has a magnitude g, which is going to be 9.8 meter per second square. Because this is magnitude, this is positive. All right. So there, to specify problems like this, you can pick any arbitrary point, say over here, just arbitrary point. It's going to be a time t there. Over here, time t equal to 0. The interesting part of this is if you oh, wow, come on, get me a black pen here. Okay, so we didn't get a black pen. So this is the initial velocity. So sometimes I would like to write initial point, and this is as a final point. Okay, and sometimes the final point time is written as t sub f rather than t. And this is written, instead of t equals 0, is written as ti. Okay, so when I shoot something, it's got some speed and some direction. So speed here normally is written as v sub 0, but you could write this as v sub I. Okay, you can also write this as v at 0 time. This is t equal to 0. And then there's this angle theta, which should be, if I'm going to be consistent with this kind of thing, so I should use same subscript to do it. So let's call it theta 0, but often it's just written as theta. Okay, so this is if you look at the velocity vector at t equal to 0, I'm just being very pedantic here, just so all these are used. So this has a magnitude v0, and then must have some kind of direction. The way we're going to say direction is pick a direction. Say this is the x-axis, positive x-axis, and this will be like a positive y-axis. So with respect to the positive x-axis is theta 0 counter clockwise. So I'm going, so if you look at old clocks, so if this is 12 o'clock, this 3 o'clock, then this clock's hand moved that direction. And I'm going from x-axis in that direction. So that's a counter to the clockwise from positive x-axis. Okay. So this is describing what this velocity is. And z-axis is coming out. So this is the xy plane. The motion will all be in the xy plane. And the z-axis, the way you show the z-axis in a plane, if this is the xy plane, with this is being x direction, this is the y direction, then the z direction is coming out. And we think of the arrow coming out, that's the z direction. It's basically, that's the direction of the z-axis, okay? And it's perpendicular to it. Rather than doing this is kind of hard to see it. So you do it this way. And over here, I don't need to follow z. So this is going to be some vx, v0x, v0y, and 0. So if I've already explained the notation for the vectors, and these are components. So the way we're going to get these components is we always go back to the position vector. Remember, so if we imagine this was a position vector with distance v and angle v0, angle theta 0, then to get the x part, we just drop it 90 degrees, and then this is going to be v sub x. So if I had like x and y, and if this was in that direction and this was the theta, some vector say a, let's call it v0, theta 0. It was like this. This will be v0x, and this one, the way I've drawn the picture here, this is going to be greater than 0, and this will be less than 0. So I'm going to make sure that over here v0x will be v0 cosine theta 0, but over here v0x will be minus v0 cosine theta 0, if this is theta 0. But if you started from positive x-axis and went all the way there, let's call it that angle theta, then this will be same thing at v0 cosine theta. So you can use this formula as long as you come from the positive x-axis, full angle. But if you got a smaller angle, acute angles like this, then you need to be very, very careful with the sign in which it's pointed and where the projection will be. Okay, so this is the warning. A lot of people make mistake in this, okay? And because people make a mistake in this, it gets tested. So physics professors like to make tricky questions where they know what kind of mistakes people are making, and so they want to make sure that we test those things. Okay, we're not being mean. We just want to figure out distance and what's the difference between people who are paying attention and those people who are just kind of memorizing and not paying attention. Okay, so this is the case. All right, let's be cool. And so so we got the v0x, so that we can break this up into its components. And over here, the v will be pointed tangent to this, right? Again, tangent to that point. And this is some arbitrary point I just picked up. So this will be the vector v at time t. Let me erase that trajectory over here. It's not as good as I was expecting. It's kind of a little slow and yeah, this is not cool. Not cool, man. This is, I'm in the middle. So this is v at t. So the equations that we worked out before, if I write them vector notation for constant acceleration a, it just turns out to be v at t equals to v at 0 plus a times t. A doesn't have time, so it's constant. And r at time t equal r at time 0 plus v at 0 times t plus half a t square. These are all vectors. So if you were looking to make this guy, this equation for the x part, because acceleration is 0 minus g 0 here, and this is the z component we don't have to worry about. So, and the v of 0 is v0x, which we did this, and similarly you should be get v0y. This will be v0y, and that will be v0y will be v0 sine theta, because this is opposite. So v0x, v0y, and then 0, and so that takes care of this equation getting separated. So that equation turns out to be vx at time t equals to vx at time 0, and a is 0, so ax is 0, so plus 0, and for the y part, vy of this t equals to v y 0 plus minus g times t. And then we can write for this equation, separate this equation, r at time 0 we've taken to be at this point, so that just 0 0 0. R at t will be x and y, but 0. So this is the z, we can ignore it, and everything else is known here. So x part will be x, and from there it's going to be 0, and that's going to be v sub x at, which is v0x, which is, if you do want it to be consistent, v0x t plus 0, because a sub x will be 0, and the y part will be from here just going to be read out y of t equal to for us is 0. And then v0 yt plus half minus g t square. Now, one complication may sometimes happen that it's not over here that's given. Maybe that it's given over here. Okay, let's just not use that, or let's use blue. So suppose the v0 was this. Oh, v0 was this, and the theta with respect to this was the theta 0. If you had this situation, then you'll have x0 here and y0 here, and which may not be the same. So sometimes we write down x0 here, y0 to include this possibility also. So these are the working equations, but they have t in them. It turns out that these two equations we can, just like just vertical motion thing we talked about last time, you can get rid of t and you will get v y at t square equals to v0 y square plus 2 acceleration is minus g y at t minus y at 0. So this is the has no t. So I keep calling this is the no t. So this is no explicit t. So in some problems you just want to have this use this to solve the equation, the problem. Okay, so let's do a new board. Okay, so board number 2. All right, so let's an example work out. So here is, I'm going to shoot at 60 degrees and at 20 meters per second. And maybe over here, there's a platform at 1 meter this height, and it's going to go land on somewhere. So we want to look at an instant before it lands. When it lands, it's going to become speed 0, right? That's because when it lands, it hits. When it hits, acceleration changes here. Over here, the acceleration is minus g. Ay is minus g. This is x and this is y. But when it hits, after it hits, ay is 0. So you can see this changed. So I can't use constant acceleration. So I have to, even if I need to know information about that point, but we can get as close to the hitting as possible, if not when hitting. So as close, so at point B, let's call point A, at close to point of hit as possible, except except the hit point. So this is the way you have to understand. So the motion will be A when it's going like that, and so instead of B, you're going to look at its cousin B prime. So the initial point is this, and final point is not B, but that's going to be the final point. So we will work out where it hits. So this, given this, the acceleration is pointed down and it is 10 meter per second square in magnitude. The question is find B, find V at B, which is not really B, but B prime. Okay, so I'll just keep calling it B, but I'll mean B prime. So not like that. I'm going to go back to the B, calling B prime as B. But you gotta understand that this is B prime. Not, we can't get the B because velocity after you hit it is 0. This is very common confusion. But that we don't mean that. We actually say it, but say how it hit, how fast it hit. But we didn't say it that we not supposed to include the point. Okay, I'm belaboring that point because it's such a common mistake. Okay, so these are two questions we want to answer. So finding B, what does it mean? Let's take a different ink. It means what's the coordinate of this point? So it will be some x and y, and the time is t. And another will be find B, find t. Okay, so when it will hit, where it will hit, how fast it will hit, those three questions let's work out, and then we should stop. This should be a prototype of every single problem. Okay, all right, so what we have, we have from here x0 is 0. Usually helps just to skip the x information separate from the y information. And we need to find xt. We'll just call it x. And yt, well, it says it's going to be 1 meter, so equals to 1. And we're just going to call it y. And v0x, from drawing this and calling this v0, is just v0 cosine 60 degrees. That makes it 20 times half is 10, and this is meter, and this would be meter per second, but I'm going to ignore units since all of them in SI units already. If they were not there, then otherwise convert them. If necessary. But don't write in the equation. Then you got v0y is v0 sine 60 degrees. And that comes from dropping on the y-axis. This part is at the origin, and whenever you drop this distance from the tail to where you dropped, that's v0y. And that's going to be 20 times square root of 3 over 2. So 10 square root of 3. Of course, ax is 0 and ay is minus 10. The t is the same. Same t in both the same. So we need to figure out t. So, all right. So that's the setup. In this x equation, so this is the x guys and this is the y guys. In the x guys, we have v xt is v0 x, because acceleration is 0 plus 0. So this turns out to be, it's going to be the same thing as 10 meter per second. How about x at time t should be equal to x in time 0 plus v 0 xt, for because x is plus 0. So if you look at this, this is 0, this is 0, this is 0, so just 10t. So we need to figure out t before I can figure out x. So this is one of the things I need to figure out, but we need to figure out t before I can. So let's look at the y. These are the only things in the x direction. In the y direction, I can get vyt equal to by at 0 time minus 10t. So we don't know t. So this gives me vyt equals to 10 square root of 3 minus 10t. We need to find this, but we don't know this. Okay, so the next equation will be yt equals y of 0 plus v y of 0 t plus half minus gt. So this becomes, this is 1, this is 0, this is 10 square root of 3, and this is minus 5. This is 10, so this is minus 5t. So this is a t square. So we need to actually, this is a quadratic equation, we need to solve this. So let's write that 5t square minus 10 square root of 3 plus 1 equal to 0. So this is like ax square plus bx plus c equal to 0. So that's how do you know that that's going to solve it pretty fast. T will be 1 over 2 times 5, 2a, minus b becomes, minus a becomes plus 10 square root of 3. Then there will be two values. Then square root of b square is going to be 300. Square of that will be 300 minus 4ac is 4 times 5 times 1. So that's 20. That's 20. That's 280. And because if 10 square 3, I'm going to pull 100, divide 100, and this is going to be 2.8. So 10 square. So pull 10 out, and that will kill with that 10. So this is square 3 minus square 2.8 plus minus. So with the minus, you get smaller values. With the plus, you're going to get a larger value. Let's go. So t1 equals square root 3 minus square root of 2.8. And t2 is square root 3 plus square root 2.8. So why do we get these two values? What does it mean? What it means is if you look at the information that went into just the y values went into, no x values, right? So at this height, there are 2 times that this height. So at this height, you take this height and go all the way across in the trajectory. So you have over here, but it was at the same height over here also. So this was, if you look at this, this was, it was here at t equals to t1, and it's there at t equals to t2. That's what those 2 times are. But we are interested in when it hits, not hits from the bottom. Maybe that would have been interesting. Maybe there's a board here going to hit from the bottom. That was the question, and we'll get this t1. But its problem is saying when coming down it hits. So for us, this is the time of interest. Both could be, depends on situation. It's not like this is always going to be of interest. No, sometimes this will be of interest. Depends on the problem, what the description is. So now we have, this is the time. So we use this guy here. So x at t2 is the one we're interested in. So I need to just adjust this. X at t2 is 10, t2 is 10 square root of 3 plus square root of 2.8. So this is definitely this. So the b is at 10. Let's call this x2. It is x2 1 0 coordinate, 1 meter, right? So we found that. We already found t, that's t2 value, which we already know. Now we have to find the velocity at b. We already know what vx is. It's independent, so we know vx. Vx is 10 meter per second. We need to find Vy. We look at over here, I could find Vy from this, but T2, put T2 there. So Vy will be 10 square root of 3 minus 10 square root 3 plus square root 2.8. Okay, so this, you open it up, then this guy will kill 10 square root of 3, 10 square root of 3 minus 10 square root of 3 minus 10 square root of 2.8. These guys cancel out, so this minus 10 square root of 2.8. So these are, so the velocity vector at the instant it hits the platform, it has these components. It says 10 and it's got minus 10 square root 2.8. And y, of course, this is the v sub z, is going to be 0. So let's look at the angle it will hit at, and let's try to get another clean. So the way we're going to get directions and things like that is you always go back to the way analogous with position, right? So velocity vector is 10 minus 10 square root of 3, 2.8 and 0. Okay, it's, of course, the unit is meter per second. So we think of these as position in analogous position. So if I gave you if I give you, if I give you the position was 10 minus 10 square root of 3, 0, how would you say which way is pointed? Well, you're going to do the x, actually x, you're going to 10 minus 10.3 minus 10.3 over here, and you'll say, hey, that's the point, that's the way it's pointed. It's the same way we're going to do this. So, but instead of this being 10 meter, it will be in meter and meter. We have to, because you're plotting v, the scale has to be meter per second. So say this is 5 meter per second. This is 10 meter per second. This is going to be minus 5 meter per second, minus 10 meter per second, and it's going to be all, this is going to be minus 15 meter per second. It's going to be minus 20 meter per second. So it's going to be somewhere here. This point will be here, and so the velocity is actually pointed down like that. And the magnitude, this length will be the magnitude, which is the same thing as speed here, will be square root of this side is 10 and this side is 10 square root of, so 10 square plus, minus doesn't make a difference because square it, if you want to put a minus is fine, minus 10 is square root of 2.8 squared. So if you look at it, this is 10, 1 plus 2.8 is 10 square root of 3.8 meter per second. Now this angle, we can say I'm going in the clockwise, same as this is clockwise. So it's going in the clockwise from the positive x-axis. So this angle will be negative by notation. So theta will be arctangent inverse minus 10 square root of 2.8 over 10. 10 cancels out, so minus arctangent square root of 2.8. If it was 3, then arctangent square root of 3 will be 60 degrees. But so it's a little bit less. So let's call it 55 degrees. I don't know. I didn't calculate it, so just leave it like that. Or 57 degrees, maybe 57 degrees, very close to 60 degrees. Okay, so we are done. It's going to go out there, and not the same height, but over here at 1 meter is going to hit it at this angle, which has to be negative. If it didn't come out negative, if it didn't down like that, if this value was not negative, the y will all be concerned, right? Because it's hitting, coming down and hitting. So up is y-axis positive, then the down part will be y-axis will be negative. The x-axis is still going to the positive x-axis, but it's coming, the y-axis is pointed up, so it's coming negative y-axis. Okay, this was a standard problem. I hope this video turned out okay, because earlier I recorded something like this and it didn't turn out okay. So this is some second recording for this. Otherwise I would be a little bit disappointed. Okay, so next we're gonna do next motion is actually circular motion. So we're going to review circular motion a little bit, and maybe we'll have to review a little bit of polar coordinates. All right, till then, bye.